thank various people for heavily advertising the talk. So anyway, just some outline of what I want to talk about. First of all, just some general background in SYZ conjecture, and then some discussion of involutions. So I feel like most people have heard me talk about this before. So I'm going to try to be brief about that, and then I'm going to try to state some theorem, and then indicate something about the proof. SYZ conjecture. Well, first of all, so let's say that X and X check are Calabi-Yau manifolds. So if they're a mirror, well, sort of really Kontsevich homological mirror symmetry conjecture says that these guys are mirror. Then one should expect that there's some kind of equivalence of derived categories. So in particular, the sort of derived Fukaya category of X should be equivalent to the derived category of coherent sheaves on X check. Okay, that's as much as I'm going to say about that. So don't worry about the actual definition of these categories. I don't really need very much about it. So then sort of, well, Strominger, Yau, and Zaslow came along, and they said, well, so let's see if we can guess a particular instance of this equivalence. So, and they had a particular motivation in doing this, but really they asked the question, so let's suppose that P is a point in X check. So then there's a sort of very easy to construct object in this derived category, which is just the structure sheaf of the point, the skyscraper sheaf at P. This, of course, belongs to this derived category. So, well, you have this sort of easiest object that you can construct. What is its mirror? Well, so their answer was, probably everybody knows, that we should look for Lagrangian tori in X. So, well, just say, so why is this plausible? So I mean, well, so let's say with flat unitary line bundle. So I mean, I think the motivation for the conjecture was just this. So I mean, if we consider Ham in the derived category, so this is somehow, you know, the derived Ham between O of P and O of P, this is canonically isomorphic to the exterior algebra of the tangent space at P of X check, whereas and it's well, if defined, if L is unobstructed, as mentioned in Hiroshi's talk, so then it's reasonable to hope. So, as also mentioned earlier, not always going to be true that well, so that HF LL, and I'm going to generally drop the flat line bundle because you can always put it in anywhere. It's not going to change anything I say. This guy will be isomorphic to the cohomology of L. Actually is a ring, of course. And this, of course, is the same as the exterior algebra on H1 of L. And so, I mean, in general, there's going to be some kind of complicated spectral sequence. So in general, there exists a spectral sequence, which starts from the cohomology of L and converges to the floor cohomology. So the claim here is that it degenerates. So that's something one can hope to happen. And I mean, well, so in this case, then of course, these two Hams look very, very similar. And in fact, seeing what the Ham of OP to itself is, you would almost guess that it has to come from a torus because it's just the cohomology of a torus. So, so then this would be isomorphism. Of course, here use the fact that kind of, the dimension of X is the dimension of X check. This is the, on the hand, it's equal to the dimension of, I don't know, equal to the dimension of, the real dimension of L. This is the dimension of Tx, P, Tx check at P. There's also the dimension of H1 of L. So these things are the same dimension. They have the same algebra structure, everything. Yeah?
From what I understand in general, there's no reason to expect the spectral sequence to degenerate. And
Right.
even if it degenerates, do we expect the ring structure on the right-hand side and the left-hand side to be the same?
No.
So what is so special about this L that makes everything work?
I'm going to try to say. So right. So I mean, not only that, but you could ask even further. How about Massey products? So similarly, you expect all Massey products on HF LL to vanish. Okay, so in fact, you kind of expect the underlying A infinity algebra of L to be formal and sort of homotopy equivalent to its cohomology as an A infinity algebra. So of course the goal here of this talk is to construct such an L. So actually, I mean, a whole family of them. for some sufficiently large class of examples of Calabi-Yau manifolds. So I'm going to just refer to this as condition star so first of all, the floor homology is defined, and so L is unobstructed, and so HFLL is actually as a ring is equal to H of L, and the Massey products vanish. So to get there, I'm going to have to talk about one more aspect of the SYZ conjecture. So, this is really kind of getting at the original motivation for trying to find out what was the mirror of that particular object. So there's a conclusion of, so back to SYZ. So after just stating the goal, back to SYZ. Their conclusion was this kind of naive question and answer, that if we find the right Lagrangian, then we can really reconstruct X, the mirror manifold, from just this sort of pair of X and L, just by kind of considering the space of all deformations. And well, that of course has to be elaborated upon. And one can consider some kind of mod equivalence this is of course something which is highly unclear how to define it mathematically, but just like when you take a point inside of a complex manifold, of course you can deform it, you get all the rest of the points of the complex manifold. So too, if you just had this Lagrangian torus and you knew what it meant to deform things in a derived category, well, you could just deform this L, and you could recover the entire set of points, presumably with an additional structure of a complex manifold of the mirror. So that was I see. So they had this sort of additional idea, which was kind of suggested by this deformation argument, which was that just the classical deformations of L, mod Hamiltonian isotopy, can be parametrized by, say, fibers of a perhaps special Lagrangian vibration. So you consider a map from X to some base manifold. So its real dimension should be equal to the complex dimension of X. And if X is simply connected, so presumably it should be, well, sorry, I mean, if X satisfies enough conditions to make it Calabi-Yau, so in particular dimension 3, but simply connected, then B should be something like a sphere. And sort of, you know, the fibers should be, they should contains a relatively open, dense, smooth Lagrangian. So I mean, in other words, the fibers could often be singular, but you should have, at least within each fiber, some kind of, you know, this fiber should be essentially the closure of some smooth Lagrangian sitting inside of X. And, you know, generically, such a thing will always have tori for fibers. So, in general, F could be pretty nasty. It could not even be smooth, but let's ignore that for the time being. So this question of whether there exist Lagrangian fibrations on Calabi-Yau manifolds has been studied very extensively, and I probably don't have time to really do any kind of satisfactory treatment of all the different people who've worked on it. There's definitely work of Mark Gross and of Ruan and many other people, and finally Joyce. And so, I mean, the result that I want to relate to is just some sort of latest development. So it was a bit difficult to actually construct Lagrangian fibrations in Calabi-Yau manifolds. So Castano, Bernard, and Matesi, we constructed a class of, let's call it C, of Lagrangian fibrations F. Well,
not singular, just like one.
Lagrange, yeah, so I'm not saying anything about smoothness. I mean, not special, just Lagrangian. I mean, there was, in the original SYZ conjecture, there was definitely a condition of special, but, you know, take what we can get. And that will be enough for our purposes. So, but in a sense, maybe one of the reasons for studying special Lagrangian fibrations is that allows you to sort of parameterize the deformations kind of canonically. But maybe a corollary of the theorem that I want to prove will be that you can still find kind of a smooth slice of the action of the Hamiltonian symplectomorphism group on the deformations of some Lagrangian. So constructed a class C of Lagrangian fibrations F. So for X, you know, for example, any 2 or 3 dimensional Calabi-Yau complete intersection in a toric variety. So in other words, many of the most well-studied cases of Calabi-Yau manifolds have such fibrations of class C on them. There are some other stuff which is in class C, and one should certainly hope that we'll be able to construct higher dimensional examples and by similar techniques, but that hasn't yet been done. Anyway, so now I'm on to involutions. So this was just some history of the SYZ conjecture. So here. Bad. So involutions, well, oh, forgot. There's two remarks I want to make about this theorem. So, or this construction. So this is a paper of 2006. So the remarks are, first of all, there always exists Lagrangian section of such a fibration. And two, so the fibers have Maslov class. This was by construction, essentially. And the second thing was that the fibers have Maslov class 0. So this is something which is not hard to prove, but it's not yet been written up orderly way. So now on to involutions. So there's a theorem. This, I think what Hiroshi was saying by other examples of involutions, antisymplectic involutions. So since one expects antisymplectic involutions whenever one sees a Lagrangian fibration, assuming the Lagrangian fibration is sufficiently nice. So let me just say exactly what the statement is, and yes.
Should I think of this involution as interchanging base and fiber, or is it?
No, I'll just write exactly what it is in just a second. So the theorem says that let X F be some fibration of class C. Let's say that let sigma be a Lagrangian section of F, and say we'll have to impose some conditions here of class C with some extra decoration. So I'm not going to write the exact definition of this class, but there's a lot of such sections, and essentially the only restriction on the section is that at sort of the codimension 3 singularities, it has to fit some particular model. But those are just codimension 3 singularities. They're codimension 3, codimension 2, codimension 3. Yeah. So essentially, it's sigma can be chosen with a large amount of freedom. Just at some isolated points, it has to behave nicely. Well, in the three-dimensional case. So in the two-dimensional case, it can be anything. So you have a Lagrangian section of class C. So then there exists a unique antisymplectic involution of the total space of the fibration So I think that was defined earlier as well, such that two conditions are satisfied. So the first condition is F composed with phi is equal to F. This means fiber preserving. and 2 phi composed with sigma is equal to sigma. In other words, it fixes the section. Okay, so what's the motivation for such a thing? So okay, this is nice in the sense because it just gives us lots and lots of examples of antisymplectic involutions, which seem to appear naturally in the context of mirror symmetry, Lagrangian fibrations. But why would one think such a thing is likely to happen? Well, probably talked about this too much already, so be brief. The motivation is that sort of the choice of a fibration F and a section sigma determines, I think this is really an idea of Fukaya, the equivalence. So I mean, a priori, if you have two derived categories, which are two triangulated categories which are equivalent, then there are many different equivalences between them. I mean, each one has its auto-equivalences. But if you choose sort of a fibration and a section, then you get an actual kind of canonical way of doing this. It's given by family floor homology or something like that. Sigma here should, determine which Lagrangian corresponds to the structure sheaf. Then,
What way is canonical?
well, in a sense that, the fiber is going to be the points, and then, if you're given any Lagrangian here, then sort of the family of floor homologies which enter the fibers is going to be exactly the sort of family, say, of fibers of the sheaf which corresponds, and you can try to group them together. So, I mean, it's still conjectural, but one should conjecture such a thing is true.
But you don't get enough points, right? That is three-dimensional.
Oh yeah, but I mean, you have local systems on the fiber, which gives you something six-dimensional. That's the way SYZ originally took care of that problem. So the choice of this information should determine the equivalence, and well then, there's this kind of very natural transformation. There's this kind of unique kind of direction reversing involution of such a category, which is just kind of, if you consider duality. In other words, you take R hom of something with the structure sheaf of X check. This defines a functor from this category to its opposite, and this should somehow be mirror to phi. Okay, and so, R hom of OX is going to be OX. This corresponds to the fact that phi of sigma is equal to sigma, and then, yes.
So presumably may have other components as well.
I'm sorry?
Presumably fixed point of phi may have other components.
It always will.
Always what I say.
Yeah, it always will. Because this is, I mean, you know sort of the way, I'm going to get there in a second, but you know the way it acts on the fibers, and it's going to have always, 2 to the n fixed points on each fiber. Only one of them is going to be the section. So there's going to be some interesting stuff going on with other fixed points. One can speculate a great deal about that. But that's what I'm trying to do here. This is going to be something as O of p shifted by n minus n. So this corresponds to the fact that phi, yeah, I mean, here it's important that you don't actually fix the fibers, but just preserve them. That leads to a kind of shift on the grading of the Fukaya category. So all this is written out at great length in a preprint of ours. Yeah, so this theorem is due to Castano Bernard, Mattesi, myself. So it's on the archive. I don't exactly understand the connection, but I'd be very interested to learn more about. Maybe we should talk after the sounds. I mean, I'm interested in that a great deal, but don't immediately see what the connection between this and that is. So anyway, right. So there's so the idea is, well, you're given this Lagrangian fibration. You have this completely sort of canonical symmetry of Lagrangian fibration. Let's try to use this symmetry to prove that the fibers of the fibration satisfy the conditions which we started out with. So I'm only going to consider smooth fibers because I don't even know how to go about beginning to define the definition flow homology for the non-smooth fibers because they're pretty badly singular. So use phi to prove that the smooth fibers of F satisfy these conditions. This would be the goal. So do I have more here? Okay. Just one more thing that I should say is that, so I want to generalize the theorem a little bit more so that we get more examples. And well, anyway, the point here is that phi restricted to L is, say, isotopic to, but I'm only going to use something much weaker than that, the inverse map of Tn. So sorry, phi restricted to any fiber is going to be sort of the same, essentially the inverse map of Tn. In other words, think of Tn as a group. There's a sort of inverse map there, and it's immediately clear from the construction that this is true. So then,
you feed back one fiber to another fiber, right? So what do you mean?
So phi doesn't. So the condition one is that sort of phi preserves the fibers.
Oh, preserves that one.
Okay, so then it makes sense to look at phi restricted to a fiber, and one can then, well, it's easy to see from the construction of this phi that, or just completely general considerations, that restricted to a fiber is just the inverse map on the fiber. So now onto the theorem part. So suppose you have contained in X is Lagrangian, so I'm not going to make any assumptions on dimension or anything here. And just assume that L is Lagrangian torus with mass left class 0. And let's suppose that there exists an antisymplectic involution of X such that phi restricted to L is let's say acting on the cohomology of L is just is the same as the inverse map. Okay. And I can put local systems there. I mean, dimension rank 1 local systems, unitary local systems doesn't change anything. Thank you. So then, first of all, L is unobstructed. Well, simply L satisfies the condition star. So it's unobstructed and it's and its floor homology is standard as a ring, and all its master products vanish. So in particular, if we apply this to any of the fibers of one of these Castano-Bernard-Matesi fibrations, we'll get they satisfy sort of the assumptions of the SYZ conjecture. So just now I'm going to go on to in the direction of the proof. So I have to introduce some, well, maybe it's going to be a restatement of the theorem. But, you know, along the way I should say something about obstruction theory, or, well, infinity algebras. I don't know. Might be. Okay, so anyway, what about infinity algebras? So I'm going to just completely follow recent book of Fukaya Oto and Ono on this regard. So I mean, given so I mean, of course, this works in tremendous generality. I'm going to only consider the Calabi-Yau case. So let's suppose we have such a Lagrangian spin. Of course, the torus is always going to be spin. So then, so to each such Lagrangian, we can associate an infinity algebra which Hiroshi talked about earlier. Okay, so this is essentially a module over some number covering lambda, and mk are some multilinear maps which satisfy certain quadratic relations, which were written earlier. So the key point is that there's a Morra-Cartan equation which was also mentioned earlier, but I'm going to say it a little bit more explicitly here. So let's say that B belongs to, so this is a graded module, so you can look at the first graded part. So for such B, we can write, well, the point of being in the first graded part is then this sum that I'm going to write is going to be of a single grading. I guess in general you could look at the odd part and the even part and so on and so forth, but I'm not going to need that. So sum k equals 0 to infinity of this business. So Morra-Cartan equation is that P of B equals 0. Okay, so right, this is star, other kind of star. So L unobstructed is the same thing as by definition. It's just that if there exists a solution to the Morra-Cartan equation. Now, in fact, so the theorem written above is equivalent to the following corollary, which is that if L Lagrangian submanifold as above, in other words, a torus which is preserved by a certain involution, then let's see, I wanted to say one more thing. Well, yeah. So homological perturbation theory says okay, so a few more things. So the first thing is that, I mean, what is the meaning of the solution of this thing? So essentially, so let's define M of L is sort of the solutions of the Morra-Cartan equation mod some kind of gauge equivalence. I'm not going to say what that is, but in a second I'll say something which makes it vanish, so you won't need to know. This is all explained in FO cubed, following their notation even. So, I mean, what this means is essentially the set of, in a sense, quantum perturbations of L. Think of this as kind of a quantized perturbations of a Lagrangian. So if there's kind of one which one solution, then this sort of, that means that there's at least one kind of quantized version of this Lagrangian, which makes sense. And if there's many of them, then it means that, well, they can all be sort of seen as perturbing this L. Deformation, or sorry, not perturbations, but I would say deformations deformations of L. Well, so another thing is that homological perturbation theory essentially says that, well, I mean, this infinity algebra is only really defined up to infinity homotopy equivalence. So, in particular, you know, the exact vector space which is given by C of L and lambda could even have differing dimensions. So, you can actually choose C of L and lambda to be isomorphic to just the singular homology of L with coefficients in the Nova quadrant. So, so in this case, and now I'm going to use the fact that I'm in the Calabi-Yau situation, gauge equivalence is trivial. Okay. So where am I going with this? I'm going to come back to the original big picture and say, so in particular, we're going to be looking at some subset of just H1 of L with coefficients in lambda. So ML is just contained in H1 with coefficients in, well, I guess I should have said lambda plus, which means, well, you have to have some kind of positive filtration for things to converge properly, but so there's also lambda plus. So the theorem says that, so you think of this as being sort of deformations of L in some quantum sense. Well, L is supposed to be mirror to a point. Well, you don't expect a point to have just a single kind of deformation. It should have essentially a maximal family of deformations. All deformations of the point are unobstructed. So if you have a point in a complex manifold, you can always deform it every which way. All infinitesimal deformations integrate to actual deformations. So the theorem is equivalent to the following corollary, which is that P is actually identically 0. So ML is actually just the same as H. Well, in a sense, I mean, it's not canonically. So, so in other words, the deformation space of L is exactly its first homology, as one would expect from mirror symmetry. So I should just mention this. So when L is a fiber of a Lagrangian fibration, this is a conjecture of FO cubed, well, actually, conjecture C. So, actually what I'm going to prove is this corollary, which is equivalent to the original theorem. So, I have a little bit of time to prove it. So here goes the proof. So the main lemma is the following, which is kind of extremely transparent if you ask me. First of all, you can choose CL, well, you can get this. You can construct this A infinity algebra. I should say construct, not choose. But I mean, of course, it's only given up to homotopy equivalence, but you can find a particular model in which two nice conditions apply. First of all, the homological perturbation lemma. So that is that C of L lambda is isomorphic to H1 of L coefficients of lambda. And two, that, well, I want to say some kind of compatibility with phi. So I want phi star of mk of x1 up to xk to be equal to exactly mk of phi star. Now I have to reverse the order, just like in Hiroshi's talk. X1. And then I have to put in a sign, which is none other than the sign of Hiroshi's talk. So I should just mention that this is not just a special case of what Hiroshi wrote, because that formula was on the assumption that phi fixes L. And here L is not fixed. But on the other hand, it's not, and phi actually is often, say, orientation reversing on L. And so one really has to think a little bit about how to compute the sign. It's not terribly difficult. Slightly confusing, though. So, I mean, the reason one should expect exactly the same sign is because, after all, phi is not just, you know, some random thing. It's duality. So I'm not going to write it because I don't have time. But essentially, putting the sign minus 1 to the epsilon and switching the order of the entries in MK is just a way of saying what the opposite algebra is. And phi is simply an isomorphism between the algebra and its opposite, which is exactly what you expect for something which is preserved by duality. So it's not at all surprising that you get exactly the same sign here, even though the geometry is slightly different. Now let's assume this. So lemma So let's just note that, well, by assumption, you know, phi star is just like the inverse map. So phi star, I'm going to stop writing restricted to, acts on H1 of L by just minus the identity. It's easy to see that the inverse map of the torus acts on H1 by minus the identity. Well, phi star acts on H2 of L by exactly the identity, because H2 is generated by squares of H1. Well, now, just note that so the degree of P of B is 2. Well, this is, you know, let's just say MK of, because, well, the degree of each B is 1, and the degree of MK, by kind of definition, is 2 minus K. And now it's just a formal calculation. So we write mk of lots of copies of B, k times. This is, well, by sort of this observation, just equal to phi upper star mk of B, because it's something which of degree 2. And that is by the main lemma, the same thing as mk sine of minus 1 to the epsilon of phi upper star B lots of times. And now, so phi upper star B is, this is just equal to minus B by this little observation. And then if one plugs in, one gets exactly minus mk B to B. And well, that's because so if I put degree of all the xi is equal to 1, then all these terms vanish, and then I have k factors of minus 1 from here, and 1 left over. The k cancel out with the, well, there's k copies of B, each one picks up a minus 1 because of the action of phi star. So then I get, well, minus 1 to the 1 plus k power times minus 1 to the k power is just minus 1. And then this implies that mk, well, it's equal to minus itself, so therefore mk of lots of b's is just equal to 0. And that shows the corollary, since it's true for all k. And well, the corollary implies the theorem essentially by some messing around with Hochschild cohomology. So I think I'll stop there.